Okay. Now we will be talking about hydrocarbons. Now hydrocarbons are a group of compounds which contain hydrogen carbon alone. Classification, we normally classify them as aliphatic compounds, aromatic compounds, and again in the aliphatic compounds we have got acyclic molecules and cyclic molecules. We also have saturated and unsaturated compounds. Now the wealth of hydrocarbons is normally obtained in the form of petrochemicals. So the petrochemicals are chemicals which are found under the surface of the earth. Petra, as all of us know, is rock, and oleum represents oil. So it is rock oil. Normally whenever they find out a deposit of petrochemicals, they drill a hole, and once the drilling reaches the place where the oil is present, it may be 2-3 kilometers below surface, there where there is a deposit of petrochemicals, they gush out to the surface. Either they gush out by themselves automatically, or they are siphoned out. So under the soil they are compressed, and almost all of them appear to be like liquids. By the time they reach the surface of the earth, a few constituents under normal conditions of temperature and pressure on the surface are gases. The remaining are in the form of liquids. Still remaining will be viscous liquids, and a few will be semi-solids. So these large group of compounds put together are referred to as hydrocarbons, and all of these are generally referred to as petrochemicals. And we say that petrochemical deposits are due to degradation of fossils. Maybe some large catastrophe like cyclone, storms, earthquake, large areas of forest could have got dumped, the earth opening up due to an earthquake. Natural disasters are such, and then the entire the forest materials get dumped under the soil, then again it is covered up under high temperature pressure. They undergo a small degradation, decomposition in the absence of air, resulting in the formation of these petrochemicals. Now let us talk about the petrochemicals. The petrochemicals are the wealth of all the hydrocarbons. All our natural hydrocarbons are obtained from the petrochemicals. As I said earlier, when they reach the surface of the earth, some of them appear in the form of the physical state of gases. These are the gaseous hydrocarbons. And the way nature, physical state of these hydrocarbons are dependent upon the number of carbons also. As the number of carbon increases, they gradually tend to become liquids, viscous liquids, even sometimes fats, paraffin wax, and semi-solids. So the carbon number is directly related to the physical state. So therefore, the first few members, that is methane, ethane, propane, butane, pentane, under normal conditions of temperature and pressure appear as gases. These are the gaseous hydrocarbons. Among these gaseous hydrocarbons, some have extensive use as fuels. The first is CNG, compressed natural gas. Compressed natural gas is the gas that we use normally in automobiles. So compressed natural gas is almost 100% methane, and it is considered to be now the present day best hydrocarbon fuel, because the number of carbon is less, therefore the pollution will be less. When you move further, they are gases. There is ethane, propane, butane. The next set of important fuels are the LPG that we use at home or industries, liquefied petroleum gas. And the main constituent of liquefied petroleum gas is butane, with small amounts of propane, small amounts of pentane. Almost 70 to 80% is butane and butane or their isomers. When you move beyond 5 or 6 carbons, then you have liquids. Normally, liquid fuels are further classified as petrol, kerosene, diesel. Petrol is a small fraction which includes carbon members which have 6 carbons to almost 10 carbons. They are put together are called as petrol. So petrol is a mixture of hydrocarbons, normally from 6 carbons to 10 carbons. Beyond 10, 11 to 15 represents kerosene oil. So kerosene oil is a mixture of hydrocarbons which contain almost 11 to 15. See, the demarcation is not very rigid. 15, 16 could be, this side could be 9 also. but generally it is referred to as the 11 to 15 fraction is referred to as the kerosene oil. Beyond 15, that is 16 to 20, 25 is represented and called as diesel. So these are the three important liquid fuels: petrol, kerosene, diesel. Petrol constitutes what? Hydrocarbons, which are 6 to 10 carbons, kerosene oil 11 to 15, diesel 16 to maybe 20, 25 carbons. So this is the basic division of the liquid fuels. Let us talk in small interesting facts about the gaseous fuels first, and then we will move on to the liquid fuels. As I said earlier, CNG, compressed natural gas, is the best present day automobile fuel gas. It contains 100% methane. The gas that we use at home is called LPG, and the main constituent is butane, liquefied petroleum gas. And we know that the gas that we use at home normally has a very foul smell. When the burner we put it on and we don't light it, the gas has a very bad smell. Actually, petroleum and petroleum products are very pleasant smelling liquids. So, to find out if there is a leak, certain additives are put into LPG. And one of the most important additive is the mercaptans, thiols. Mercaptans have a foul smelling materials, RSH. So C2H5SH, ethyl mercaptans, ethyl thiols. These are the general ingredient used along with LPG for leak detection. So that is why we always, whenever we put on the burner, if you don't light it, you have the bad smell, and then immediately you know that the gas is open. So to prevent any kind of accidents, this LPG is mixed with a small amount of mercaptans. When you move to petrol, now all of us know petrol is a mixture of hydrocarbons normally containing 6 to 10 hydrocarbons, and these together mixture is called as petrol. Petrol we normally use in our automobiles, and the petrol that is used in automobiles have an engine which is generally referred to as the internal combustion engine. In an internal combustion engine, what happens is the petrol air mixture is compressed. When it reaches the maximum compression, a spark plug ignites the mixture, it burns, and on ignition it expands, and then you have work done. So this is the normal way in which an internal combustion engine works. That is, there are few cycles in it. One is the compression stage, then the ignition stage, then the expansion stage. So this is the smooth way in which an or normal petrol engine works. There are certain petrols which are good and certain petrols that are bad or poor. How do we differentiate between good petrol and bad petrol? As I said earlier, all hydrocarbons have to be first go and make a compression stage. On compression, maximum compression is achieved. At that point of time, a spark is produced by the spark plug. It ignites, and then maximum expansion is done. So efficiency is the compression expansion ratio. The efficiency of an engine is the compression expansion ratio. Maximum expansion, that is the best fuel. Now normally what happens is, if our fuel is not good, what happens? When the compression stage occurs, beyond a point of time, place, it cannot be compressed further. The fuel cannot be compressed. It is supposed to compress till here. Halfway down it cannot be compressed. When you try to compress, it becomes very hot, and automatically it catches fire. Spark plug does not produce a spark. Even before that, a premature ignition takes place and it expands. Now the machine is not ready for it. It is a premature ignition. There is a metallic sound, and this metallic sound is called as knocking. So knocking is produced if the fuel is poor. So they analyzed the types of fuels and came to a conclusion as what is the reason for the poor fuel. It was found that branched fuels can be compressed more because they occupy lesser volume. Straight chain fuels, hydrocarbons, cannot be compressed beyond a point. So their compression stage is less. So straight chain fuels are found to be poor fuels. Branched isomers are considered to be better fuels. So this is the main thing that they came to understand when they analyze the quality of good fuel and poor fuel. Now, for example, I write this compound octane, CH3CH2 CH2, CH2. This is N-octane. And look at this. This is 2,2,4 trimethyl pentane. 2,2,4 trimethyl pentane. Both contain 8 carbons. They are isomers. This is branched, this is straight chain. So this can undergo better compression than this. This is a better fuel than this. So there are two types of fuels, branched fuels and straight chain fuels. Straight chain fuels are poor fuels and branched fuels are better fuels. Based on this logic, there is a scale for associated with the quality of petrols, and that scale is referred to as the octane scale. Octane scale is a measure of the quality of petrol, and it has a 0 corresponding to N-heptane. It has an 100 corresponding to 2,2,4 trimethyl pentane. So 2,2,4 trimethyl pentane is considered to be a good fuel because it is branched. So this scale is called as the octane scale. Now suppose if the rating of a fuel given to us is 80, if the octane rating is 80, what does it mean? It means that its quality is equivalent to a mixture of 80% of 2,2,4 trimethyl pentane and 20% of N-heptane. This scale is referred to as the octane scale. Good fuels will have higher octane rating. Similarly, the aviation fuel that we use for aeroplanes, its octane rating is above 100. It has to be very good fuel, so its rating is above 100. So this is called as referred to as the octane scale of the petrols. So we come to understand that a straight chain fuel is a poor fuel, but when you dig up the petroleum well, you get a mixture of such straight chain fuels as well as branched fuels. So now it is our job to have good fuel. If you need to have good fuel, then naturally what we must do? We must be able to convert the straight chain fuel into branched fuels. This process of converting a poor fuel into a better fuel is called as reforming. So reforming is the process where the octane rating of a fuel is increased. How can reforming be normally achieved? By introducing branching. So a straight chain fuel can be made branched and then therefore it will become a better fuel. So or it can be made into cyclic compounds. Cyclic compounds are smaller compounds, therefore that also will have a higher octane rating. So these are the two methods, important methods, or even aromatization. That again is another method of improving the octane rating of a fuel. Okay. Earlier on, to increase the branching, they used to add tetraethyl lead. But tetraethyl lead, when added to petrol and inside the combustion chamber, what happens? The ethyl will get converted, tetraethyl lead's ethyl part will become free radicals. It will introduce branching in the straight chain compounds and make it branched, break it and make it branched. And therefore, this will lead into what? Lead to what? Extensive branching, and this branching will lead to better fuels. Now, this is one way. But the main problem about this is, once you start using tetraethyl lead, lead is deposited inside the cylinder, and to eliminate the lead, we have to add certain compounds, some sulfides. But then what happens? Lead is expelled out of the as the output from the combustion chamber, and it through the exhaust comes out and the atmosphere is polluted with lead. So nowadays they are done away with tetraethyl leads. Nowadays this is carried out, this kind of reforming is normally carried out in the refinery, and inside the refinery branching is introduced and thereby we make better petrol. So this is an interesting thing that you must know. Tetraethyl lead is not used nowadays, reforming is nowadays carried out in the refinery itself. Cetane number. Just like octane number for petroleum fuels, there is a gradation for diesel fuels and it is referred to as a cetane number. In an the main difference between a diesel engine and a petrol engine is the petrol engines are internal combustion engines, whereas the diesel engines are called as compression engines. Here the air is compressed. The air is compressed inside the chambers, and once the maximum compression is achieved, then a fine jet of diesel is sprayed, and then in the hot condition the diesel should automatically catch fire and expansion takes place. So, the compression engine, there is no spark plug, ignition takes place automatically. So, here what happened in petrol is combustion should not take place automatically. It should be done only on the completion of the compression stage, only by the ignition of the spark plug. Here no spark plug is there. The compression chamber is so hot enough, so maximum compression of the air is produced, and at that point of time it is injected, diesel is injected into the hot condition, and it should automatically catch fire. So, in cetane, the cetane number, the quality is judged upon its ability to catch fire automatically immediately. So, here it is found that in the cetane scale, just like in the octane scale, there is a 0 and there is a 100. Here the 100 represents N-hexadecane, and N-hexadecane is referred to as cetane, and 0 represents methyl naphthalene, which does not catch fire by itself. So, this is the cetane scale. In cetane scale, 100 is represented by N-hexadecane and 0 is represented by naphthalene. So, suppose you get a fuel whose cetane rating is 80. It implies that its quality is equivalent to a mixture of 80% of N-hexadecane and 20% of methyl naphthalene. So, this is how the diesel engines graded and rated. We are going to study now and understand how a refinery works. So, the crude oil is a mixture of all the hydrocarbons that we extract from the earth, and these are separated by a method called as fractional distillation. There is a large tower. In the large tower, the crude oil is burnt, heated actually, and on heating it gets converted into different components, and these components are separated. This is the diagrammatic representation of the refinery. So, the refinery at the lower end, the entire crude oil is warmed, heated, and as lighter things which have got lower boiling point come out. First that comes out is the gas. These gases normally have 1 to 5 carbon systems, and their boiling point is less than 40 degrees centigrade. These are the gases that we normally use either on the automobiles as CNG or at home or industry as liquefied petroleum gas. These are bottled inside cylinders and under high pressure. We use it at home and in industries. So, this is the first fraction. Below that comes the first liquid fraction, and liquid fraction is petrol. Petrol is a mixture of hydrocarbons that starts from 6 to almost 10, and their boiling point ranges around 20 to 70 degrees. These are commonly used in automobiles, in internal combustion engines that we discussed earlier. After that comes naphtha. Naphtha is a constituent which has a boiling point of 70 to 160 degrees. It is a larger hydrocarbon. These larger hydrocarbons are broken down to give smaller hydrocarbons like this. These are exclusively used for making polymers like plastics. Next comes kerosene oil. Kerosene oil is a fraction that is used as an aviation fuel and is also used in rockets. That is the next liquid fuel. It is also used for burning, for illumination in lanterns and lights. Then it is followed by diesel. Diesel is a 250-350 degrees centigrade fraction, and it is also a fuel. It is a larger chain hydrocarbon. It is used in compression engines. It is used in trucks, buses, lorries, etc. as a fuel. After that is the residues. The residues are generally called as fuel oils, and they are commonly used in ships. Then it is followed by more dense liquids which are called as oils, which we use in the vehicles. Then it is followed by paraffin wax. Paraffin wax normally we use for polishing.
So these are the main constituent. Below that comes a thick mass called bitumen. Bitumen is normally used for the surface coating on roads. The tar that we normally call is the bitumen. Bitumen is a very high large hydrocarbon chain. It is also used as a surface coating to prevent seepage of water on top of roofs, etc. So these are the different fractions, and all these are obtained from crude oil. On refining crude oil, we get all these different components. When we extract the petrochemicals from under the ground, earth, we get a mixture of hydrocarbons, and this mixture of hydrocarbons contain smaller hydrocarbons, that is hydrocarbons that contain 5 to 10 or 20 carbons, and a large number of hydrocarbons which contain 30, 40 or 80 hydrocarbons in it. And these higher hydrocarbons which have got more number of carbons have got less use. The main use of this petroleum is as fuels, and these fuels require smaller hydrocarbons, but we get 20-30% of very high number of carbon hydrocarbons. So these higher hydrocarbons do not have as much use as a fuel. Because the demand of fuel is so large, they thought of a process wherein they could break the higher hydrocarbons into smaller hydrocarbons into fuel quality hydrocarbons. This process of breaking down larger hydrocarbons into smaller hydrocarbons is called as cracking. Dodecane, a 12 hydrocarbon compound, is broken down into octane and butane. Octane can be used as a petroleum, as a petrol, can be as petrol, and butane is used for making polymers. This can break in different possible ways, because we are applying pressure, we can't know, we can't predict which way it will break. So different components are obtained. So when you break this 12 carbon system, the different components each have got, because there are lesser number of hydrocarbons, carbon compounds, they have got very different uses. But always during cracking, if you have 12 carbons in the starting compound, the product also, the broken products also will have 12 carbons. The two important methods of cracking is thermal cracking as well, then catalytic cracking. Thermal cracking is normally done at high temperature and high pressure. Catalytic cracking is done at a slightly lower temperature and pressure in the presence of a catalyst. In thermal cracking, we use 750 degree centigrade temperature and 70 atmospheric pressure, wherein a larger hydrocarbon is broken down into smaller, simpler fragments. So from the refinery that we get, the crude oil which contains a large amount of higher hydrocarbons are broken down. In the catalytic cracking, what we do is a lower temperature of 500 degree centigrade is used, and zeolite is used as a catalyst. So at this pressure and temperature, because the pressure is less here, it starts breaking, just like in the case of thermal cracking. So thermal cracking is more costly, because the pressure and temperature are high, and we are talking about components which are highly inflammable. So therefore, the use of catalyst for making lower hydrocarbons is generally preferred. So remember, always there are two methods of cracking: thermal cracking and catalytic cracking, and zeolite is normally used as the catalyst.
From the outside, a refinery might look like an endless maze of pipes, chimney stacks, steel columns and vessels. The fact is that oil refineries are highly sophisticated industrial facilities, transforming crude oil into valuable products used in a myriad of applications. The process starts when crude oil, extracted from the ground and transported by ship or pipeline, arrives at the refinery. Crude oil is first heated at various temperatures in an atmospheric distillation unit to separate it into different fractions. In simpler refineries, the resulting components are further processed to remove impurities such as sulfur and modify their physical or chemical properties to make them suitable for incorporation into final products. Then the blending comes in, mixing in different components and additives to prepare the finished products that are familiar to us all, such as LPG, gasoline, diesel and jet fuel.